Okay, let's get started in chapter 1 with some logic. So here it is in the book, chapter 1. So we'll go through these sections. And also here are my notes. So yeah, you should go through both. So this first section, 1.1, propositional logic, deals with propositions. Okay, yeah, so a good way to think about propositions, yeah, we're used to variables like x that can represent any number. Well, propositions, yeah, they're a different kind of variable, much simpler. They have only two possibilities. They're either true or false. Okay, so not numbers, not yet. True or false. So some examples. Yeah, we usually use P, Q, maybe R for propositions. So here's a simple proposition. So this proposition says that 3 plus 4 equals 7. And in some sense, yeah, it doesn't really matter what it says. We really just need to know, is it true or is it false? This equation is true, so P is true. Example 2, Q says the Earth is flat. Well, yeah, that's certainly not true. So Q is a false proposition. All right, so these examples so far, they're saying something, and then you can check, is that the thing they're saying true or false. But not everything is a proposition. So R also says something, but it says x equals 2. And this is not really, it is saying something, but it's not saying something that we can check. It really depends on what x is. Okay, so this doesn't count as a proposition because it's not true or false. Example 4, yeah, another example of something that's not a proposition. So this is not a statement, it's asking a question, who are you? So it's not a proposition. And just a couple more, yeah, so x equals 12. Well, here x, it's not a proposition, it's a number. Example 6, so T says 1 is less than 2 and 3 is less than 10. Well, yeah, if you think about it, yeah, these are both true, so together this is a true proposition. Okay, so T is true here. All right, so not everything is a proposition. It's just, remember, yes, so propositions, they have to be true or false. And yeah, they can't be both, just one or the other. Just like our usual variables x, if they take a value, they have to just take one, the value of one number. All right, so yeah, just like the rules of arithmetic tell us how we can combine numbers, the rules of logic tell us how we can combine propositions. Okay, so this is propositional logic in this section. Yeah, maybe the simplest thing you can do with a number is switch its sign, take the opposite, and you can do the same thing with propositions, so that the idea of negation is just to switch the truth value. So we have this notation for negation, so it's this strange, yeah, it looks a bit like a minus sign, but it's got an extra piece. And the way to read this is not P. Okay, so P is true, then not P is false. If P is false, then not P is true. It just switches, it takes the opposite truth value. So in words, not P says, it is not the case that P. So whatever P is saying, this gets to the opposite. So for example, if P says, I own a Ferrari, then not P says, it is not the case that I own a Ferrari. In other words, I don't own a Ferrari. That one's the true statement. Well, for me, but for somebody else, so not P could be false. All right, so negation, that's our first logical operation. Okay, the next operation is called conjunction. So this takes two propositions, say P and Q, and we use this symbol, so like an upside down V, for conjunction. And the way to read it is P and Q. So like one of our examples earlier. So this means P and Q. The way I remember it, you could, oops. Sorry. Think of this as like a capital A for and. Okay, so this is a new proposition. We're combining two propositions to get a new one. Okay, and so is P and Q true or false? Well, it depends on P and Q. So it's true if P and Q are both true, otherwise it's false. So this and means, yeah, these two guys have to, P has to be true and Q has to be true for the conjunction to be true. Otherwise it's false. Example, suppose P says 1 is strictly less than 3, and Q says 4 equals 5. Then what about the conjunction? P and Q says 1 is less than 3 and 4 is less than 5. 4 equals 5. Oops, this keeps happening. So this one's true, this one's false, and so the conjunction is false. So the conjunction would only be true if both of these were true, but Q is false. So yeah, it's conjunction. Yeah, maybe it's a little bit like multiplication. Disjunction, the next operation, maybe a little bit like addition. So this looked more like a V. So for disjunction, this means P or Q. Okay, and the way this one works, so this new proposition P or Q is false if P and Q are both false, otherwise it's true. Another way to say that is if P is true or Q is true, or they're both true, then P or Q is true. The disjunction. Yeah, this is inclusive or. It includes the both being true case. We'll see another version. So for the same P and Q as before, P saying 1 is less than 3, Q saying 4 equals 5, then the disjunction P or Q is true. It's just, yeah, one of these is true, yeah, the first one, so P or Q is true. But you can make a different construction. You could look at not P or Q, and this would be false because not P is false and Q is false, so the disjunction is false. Okay, yeah, it's starting to get complicated. So even though these propositions can only take two values, true or false, then it can get complicated when you're combining them. A good way to see what's happening is using truth tables. Okay, so looking at all the possibilities. So here's the truth table for conjunction, for and. Okay, so this looks at the different cases. So if P is true and Q is true, then P and Q is true. So that's the first row. And yeah, you look at the other cases, the other possibilities. If one of P and Q is true and the other false, or if they're both false, then P and Q is false. And or looks different. Well, the first piece here, we're setting it up the same way, listing the possibilities for P and Q. But the third column is different. So P or Q is true in more cases, every case except when P and Q are both false. Okay, so these tables may be the best way to see what these operations are doing. So here's an example. Suppose P is true. By looking at the tables, is it possible for P and Q, or P or Q, to be false? So let's take a look. So we'll look at and first. So suppose P is true. Okay, so we're in the first two cases. Is it possible for P and Q to be false? Yeah, so it's false in this case. Okay, so the only way that can happen is if Q is false. Okay, so if P is true, the only way P and Q can be false is if Q is false. Okay, how about the OR case? So if P is true, we're in these top two cases. Now it's not possible for P or Q to be false. It doesn't matter what Q is, this is always going to be true. Alright, so that's AND and OR. Let's look at two more operations. Yeah, I said there was another type of OR. So exclusive OR is the same as the previous OR, except it's false when P and Q are both true. Okay, so it excludes that case. It has this notation, so a plus sign with a circle, so that means exclusive OR, and it's true exactly when P and Q have different truth values. So it's false if P and Q are both true or both false, then exclusive OR is false. And one last one, implication. How does this one work? So for propositions P and Q, then we use this notation for implication and read it P implies Q. Okay, so just an arrow pointing right. Okay, so this is a conditional statement. How does it work? Well, it's basically it's always true, except in one case when P is true and Q is false. Okay, let's look at its truth table. Yeah, so here it is, P implies Q. Yeah, it's always true except in this one case. So if P is true and Q is false, then the implication is false. Okay, you can't have something true implying something that's false. That's not what we want. So true implies true. That's true. And also, yeah, this may be confusing case. If something is false, then it always implies something else. So if P is false, then the implication is also always true. And yeah, here again, this is the exclusive OR, so it's this one's true only when P and Q take different truth values. Alright, so this implication, yeah, it's very important when we're looking at logical reasoning later and proofs. So if the implication is true, then the truth value of P tells you about the truth value of Q, well, at least when P is true. So if the implication is true and P is true, then Q must be true. So if you had a series of implications, then you could make a proof. Just starting with something that's true, you can make a proof and prove lots of other things are true. Alright, yeah, then So it's basically it's a simple operation, but yeah, then when we start thinking about it in English, it maybe gets more confusing. Okay, so P implies Q. Another way to say it is if P, then Q. We're kind of switching it around. Q if P is the same thing. Also, if the implication is true, if P implies Q is true and Q is false, then P must be false. Okay, so if the implication is true and Q is false, then we're in this bottom row, P has to be false. So we can also write this implication as P only if Q. Okay, because if Q is false, then P has to be false. So for P to be true, Q has to be true. Alright, so time for an example. Let P be the proposition I passed pre-calculus. Let Q say I can take calculus. Then the implication P implies Q, just in English, yeah, it's I passed pre-calculus implies I can take calculus. So that looks like a true implication. And so just rewriting that using our different ways of expressing that. So we can equivalently say if I passed pre-calculus, then I can take calculus. Okay, so that's using this this way of writing it. I can take calculus if I passed pre-calculus. That's this one. And then maybe you have a slightly confusing one. I passed pre-calculus only if I can take calculus. So that's this one. Okay, so they're all really saying the same thing. P implies Q. And one last example. Is this implication true? The Earth is flat implies 3 plus 4 equals 7. So if we look at these two propositions, yeah, the Earth is flat, that's false. 3 plus 4 equals 7 is true. So the answer is yes, this is a true implication, even though it certainly seems strange, but if the first proposition is false, then the implication is automatically true. So we're in this this situation here. So the implication is true. So the Earth being flat does imply 3 plus 4 equals 7. The Earth being flat also implies 3 plus 4 equals 10. So this implication is also true. False implies false is true. All right, yeah, so you sometimes have to make a distinction between what makes sense in English and what makes sense in these mathematical propositions. All right, but yeah, well, we're learning the way computers think, so this is the mathematical, the computer logic. All right, so yeah, we're just working our way through this this first section. So you can take a look in the book. Yeah, some more examples of propositions, not propositions. Here's Aristotle. So yeah, he developed this propositional logic. So again, yeah, we looked at negation. Okay, conjunction, disjunction, the truth tables. So here's George Boole. Yeah, he developed the rules of logic more recently. Conditional statements. Yeah, P implies Q. So yeah, we kind of only touched the surface. Yeah, there are lots of other ways to express P implies Q. Yeah, you can also talk about necessary and sufficient conditions. So we'll look at that as well. And yeah, here's a nice example. So this politician is running for office, and he says, if I am elected, then I will lower taxes. Okay, so he's making this implication. The first proposition, P, says, well, it depends on him being elected. And if he's elected, then Q says he's going to lower your taxes. Okay, so if he does get elected, then you expect him to lower your taxes to make this true. Otherwise he lied. Otherwise he lied to you. But if he doesn't get elected, what do you expect? Well, yeah, you don't expect him to do anything, right? So if the first proposition turns out to be false, then well, maybe he has some power, maybe he can lower your taxes, but you don't expect him to. So the implication is not saying anything if he doesn't get elected. Okay, so that's the tricky case we looked at. If the proposition, the first proposition, is false, then yeah, the implication is true. It doesn't matter if he lowers taxes or raises taxes. Okay, so if he doesn't get elected, then this is automatically going to be a true implication. Okay, so some more examples here. Alright, so that'll do it for the first part, so we'll look at more